Hi everybody, welcome back to AP Chem After Hours. What? Here we go. We're going to talk about reaction mechanisms today. So, we have already talked a lot in kinetics about rate laws. How to find a rate law, how to write a rate law, the difference between differential and integrated. We're going to just do a little bit of review of some of the other stuff that we've talked about before we get into the meat and potatoes for this lesson. Or faux meat and potatoes, or just potatoes, because potatoes are great on their own. Eat what you want. Okay, so first things first, we know that if a reaction is going to occur, you gotta have your reactant particles hit each other. So they gotta collide in order to initiate this bond breaking and bond making process, right? So we know that your particles have to hit each other, and there's a couple of caveats that have to be true, right? So your successful collisions, make sure that your reactants don't hit each other with just enough energy. That part has to be true, but they also have to be at the correct orientation when they hit each other. That's kind of the trickier part, right? You can hit each other if you're running as fast as you can at your buddy, and you're going to hit each other and it's going to hurt, but that doesn't necessarily mean that a reaction is going to happen if your two particles do that. They have to hit each other in the right orientation. So another point about this energy is we know that the energy required of these collisions must be greater than the activation energy for a reaction. That's your barrier, right? It's the minimum amount of energy that's required of those particle collisions. So they actually start breaking your reactant bonds and forming your necessary product bonds. We've taken a look at a lot of different potential energy diagrams, right? So this one we're going to also take a look at and kind of label a few things on it. First things first, energy of our reactants. I'll just start with blue, why don't I? So reactant energy is starting out at this line here. This is the potential energy that's stored in the chemical bonds for our reactant particles. The energy of our products is this value right here. So after our reaction happened, C and D, our products, are going to have lower potential energy than the reactant particles did. So stop and think about what you know about thermodynamics that we've looked at before. Is this reaction exo or endothermic in the forward direction? Is that favorable or unfavorable? So one thing that's going to help us label that is going to be our change in enthalpy, so our bond energy, right? The amount of energy that our reactants had minus the amount of energy that our products have, there's our delta H. Because we're ending in a lower potential energy state, there must be energy being released to the surroundings. Therefore, this is exothermic, resulting in a negative delta H value, which we know is favorable. So I'm going to also have us label activation energy. We have only ever labeled activation energy in one direction on potential energy diagrams. So this asks us to label two, one for the forward reaction and one for the reverse reaction. So the forward reaction would mean it's as written. Our reactants are A plus B, and our products are yielding C plus D. So forward reaction as written, but we know that reactions can occur in two directions. The reverse reaction would then be if we flipped it. Products become reactants, so C plus D would yield A plus B. So for the forward reaction, the activation energy is the energy at which our reactants start all the way up to the peak of this graph, EA. I'm going to label it EAF, so we know it's the forward one, just to make sure we got it, right? But if we reverse this reaction, what we'd really be doing is just flipping where our products and our reactants are. So how much energy would that take? Well, if I were going in that reverse direction, my reactants would be starting at this energy here, and still going up to that peak value. So this would be the activation energy for my reverse reaction. So stop and think, if you reverse that, what's going to happen to your enthalpy? Now you're putting your products in a higher energy state, a higher potential energy state. So what does that mean? Well, it's endothermic. The reactants would have to absorb heat from the surroundings or energy from the surroundings in order to make this thing happen. And this is an unfavorable process. So remember, if one direction is exothermic, the other must be endothermic. And you can kind of prove it just by looking at the potential energy diagram. Okay, so review of potential energy diagrams. Good there, right? Okay, now let's take a look at these guys. We've looked at these a little bit. These are our Maxwell-Boltzmann distributions, or our Maxwell-Boltzmann curves. Remember, what these are showing you is your array of molecules, the numbers of molecules, how they're distributed in their amount of kinetic energy at different temperatures. So the red line represents temperature 1, the black line represents temperature 2, and we're told that temperature 1 is less than temperature 2. So what does that mean about T2? This is our high temp, or higher, I should say. We don't know if it's high. All we know is that it's the higher temperature curve. Okay, so now that we've kind of got basics ideas about that, let's take a look what the question's asking. It asks us to explain, using the curve, why very few collisions at any given temperature are successful for this reaction. So let's go back and take a look at our curve a little bit more. Remember that these peaks of our curves represent the average number, the average kinetic energy of our molecules. So that's where most molecules will hang out, at these points here on our curves. In order for us to be able to think about if a reaction is going to happen, we need to know about the orientation and the energy of those particle collisions. Particles have to collide with enough energy to get over that activation energy barrier, and that happens to be at this point on the curve. So why does it make sense that at any given temperature, very few collisions are successful? Well, look at where the majority of your particles lie. The majority of your particles in both cases are under these sections of our curves. Very few particles are exceeding this activation energy barrier. So, why can we explain this? Because the activation energy is very high, so the probability of collisions at that temperature would be quite low. I'm not going to take the time to write that out. You can pause the video and write it out, but I feel like if I did that, it would take forever. Okay, so then the second part asks us to explain why the same reaction can happen at two different temperatures, but at the higher temperature, why is the reaction rate higher? So meaning, why is the reaction faster if you're at a higher temperature? Again, let's go back to the activation energy. What we're comparing is the area under these two curves. For the lower temperature curve, I'm going to highlight everything under that area in orange. The probability of a successful collision is only in this little area here. So I only have this little area where a collision is likely to be successful. But if I take a look at the higher temperature, now my molecules are spread out over all of this distribution, all of this area here. So what that's showing us is I have more molecules that are likely to have that energy, so there's more likely to be a successful collision. More collisions are likely to happen, so therefore more successful collisions are likely to happen. And again, why is that? Because our particles are moving at higher temperatures, so they're moving faster, they've got more kinetic energy. Okay, again, I'm not going to take the time to write that out. You guys can. Okay, so this next section is about catalysts. We talked a little bit about catalysts at the beginning of the unit when we were talking about ways to speed up a reaction. I'm going to ask that you pause the video here and you go into Canvas into this assignment. Open up the slide deck. There are a couple videos that I want you to watch. And the slide deck will help you kind of work through like this section of your packet. But really what you're going to be looking at to help you determine what the purpose of a catalyst is and how it helps you speed up the rate of a reaction is this decomposition of hydrogen peroxide reaction. So hydrogen peroxide has the formula H2O2. It is aqueous. You really only see hydrogen peroxide in concentrations of like 30% and lower. I think I talked to you in the video about the percentage that I used. I believe it was just regular 3%. But you're going to take a look at this as it decomposes. So it's going to decompose to produce oxygen gas, which is a Hofbrinkel, and water. So your first step is to write this out and then balance the reaction. Then what you're going to do is work through the slide deck to kind of help you fill out this next section to learn about what the purpose of a catalyst is. So pause this video, go do that, and then I'll see you in a little bit. Ba, 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 ba. Okay, I'm assuming you all did that and we're good and studious children. Okay, so welcome back, everybody. Now that you've learned about the purpose of catalysts and have seen like how incredibly cool they are, it's important that you know the most important thing, I guess, to know about catalysts is that they do help speed up reactions by opening up a new reaction pathway that has a lower activation energy, therefore making the probability of your successful collisions much, much higher. So now we're going to take all that information that we kind of learned and talk about something called elementary reactions. You actually have already seen a little bit of this because we did our thermo unit first, and we talked about Hess's law in that unit. So, what the heck is an elementary reaction? Why are we talking about it now? Most reactions occur by a series of steps that we call a reaction mechanism. So think about what you know about the word mechanism. A mechanism is just like a way something occurs, a way something happens, right? So reaction mechanisms just talk about the way reactions happen. Reactions can have one step or multiple steps. Each of those steps that's in a reaction mechanism is called an elementary step or an elementary reaction. If, for example, you had a one reactant step, meaning there's only one reactant in your entire reaction step, you call it unimolecular. Uni meaning one, molecular meaning molecule. So an example, a general example is what you can see here if you just had A as a reactant that then produced products. What you saw up here in this example here, the decomposition of hydrogen peroxide, that is a unimolecular reaction. Hydrogen peroxide is your only reactant there, right? Okay, so unimolecular, one reactant. In these cases, your reactant has to be activated by the surroundings to then convert to a product. Since your rate is only dependent upon the one reactant, your rate law for a step like this would be your rate constant K times the concentration of your reactant. I'm just going to call it A because that's what I used in my general example above. So let's say instead you had a two reactant step. What's a prefix you know for two? Bi. So this would be a bimolecular step. Remember that for reactions like this, you could have a product with a reactant, with a coefficient of 2. So it's doubly dependent upon that reactant. Or you could have two different reactants. So my examples there are A plus B or 2A that would yield your products. So for these cases, your rate would be dependent upon both of those products. So your rate constant K. For the first reaction, it's dependent upon concentration of A and concentration of B. So there would be your rate law. Your other example for the second one would be your rate equals rate constant K times the concentration of A squared. It's doubly dependent upon concentration of A. Lastly, you could have a three reactant step. These are called termolecular. For both bi and termolecular mechanisms, you have multiple reactant particles. So because we know about collision theory, we know that those reactant particles would need to collide with each other with sufficient energy in the right orientation to then produce your products. So what that means is for a 3-reactant system, that's super duper rare. That's really hard to happen, right? 3 things coming together with enough energy in the right orientation. That's crazy. Have you tried to get a group of 3 people to agree on anything? Wild, takes forever, right? Same thing with your reactant collisions for termolecular. So that doesn't mean it can't happen, just means it's rare, unlikely. We can write a rate law for this. It would be your rate constant K. And then for the example, the first example that I provide you, it's dependent upon the concentration of each of those reactants. It could potentially be doubly dependent upon one reactant and singly dependent upon another. So another example would be the second example there, A squared times concentration of B. So there's your 3 types of reaction mechanisms that you could potentially run into. So how can we use these? What kind of chemistry are we going to do with them? So your elementary steps in your reaction mechanism must add up to your overall reaction. Duh, right? You can't just randomly add stuff in there and then it just magically disappears. It has to be used for a purpose. It has to do something, and it has to add up to your overall reactants yields products. Law of conservation of mass matter, right? So let's take a look at this example here. Let's say that you have this reaction that occurs via a 2-step mechanism. We looked at something similar to this before, like I said, when we did Hess's law. But in this 2-step mechanism, you'll see that we produce this N2O2 molecule, and then immediately in the next step, that N2O2 molecule gets consumed. It gets used. So that means this thing is what we call a reaction intermediate. Intermediates are created in one step and consumed in a later step. So what this means is intermediates do not show up excuse me, in your overall reaction equation. You produce it in one step, use it in the next step, so overall it's not important, right? So in our overall equation, we get rid of any reaction intermediates. So if I add down, I have NO plus NO, so overall I have 2 NOs. My oxygen is also a reactant, so that comes in here. And then what's left on the product side is just 2 NO2. So that would be my overall reaction that you see here. Another species that you could see show up in a chemical reaction is a catalyst. So let's take a look at an example for what a catalyst would look like in a reaction mechanism. So this time you're given that this is a 2-step reaction, but you're only given one of the steps and the overall reaction. So you kind of have to like backwards map to see what you're missing. So I see O3 appear as a reactant, and it's here as a reactant in step 1. So that's pretty good. I don't see any O, so that must mean that I need some O present in step 2. I see O2 as a product in step 1, O2 as a product in our overall, but what's the problem? In the overall, I'm producing 2 moles of O2, whereas I only have 1 in step 1, which means there must be more O2 in step 2 to add up to those 2 moles. Okay, now other issues that I'm kind of noticing here. NO2 and NO do not show up in my overall reaction equation, which must mean they've got to be used somewhere else. That's going to lead to me ending up canceling them from my overall equation. So that means if NO2 is here as a product, the only way for me to cancel it is if it's a reactant in a following step. So it must mean it shows up here. Same for NO, nitrogen monoxide. If it's a reactant in step 1, it's got to show up later as a product so I can cancel it out on that side. So let's go through and kind of label these things now and check and make sure we've got everything we need. NO shows up in our step 1, but it also shows up later as a product. This is not an intermediate. Intermediates have to be created, then consumed. This shows up in step 1, but then shows up later again in step 2. So it's still going to be canceled out, but why is this canceled out? Because it is a catalyst. Catalysts are used at the start of a reaction to speed up a reaction step, but they are reproduced later in the reaction, so we get them back. Because of that, they're important to the reaction, but they don't actually participate in the overall reaction, so they're canceled from the overall reaction equation. So NO, nitrogen monoxide, must be a catalyst. It shows up at the beginning, it gets reproduced at the end. So what does that make NO2? So NO2 is produced in one step and consumed in the next. That means NO2 is an intermediate. Based off of everything else, if I add straight down, I end up with one ozone, O3. I end up with one O, singular oxygen atom, and then I end up with 2 molecules or 2 moles of elemental oxygen, O2, on the product side, leading to my overall reaction equation. So that still looks good. Okay, so when you draw a potential energy diagram for things that have multiple steps, what you have to kind of consider is all of those peaks. Every elementary step is going to get a peak in your potential energy diagram. But that doesn't mean that every step is going to occur at the same rate. They're each going to have their own activation energies, and they each can occur at different rates. So, you might notice that in this reaction right here, you have these slow and fast words written next to each of these elementary steps in your reaction. Have you ever heard the phrase, you're only as strong as your weakest player? Like if you're talking about a team, it's the exact same thing for a reaction mechanism. Reactions only occur as fast as their slowest elementary step. So the slow step in a reaction mechanism is called your rate determining step. Determining step. You can abbreviate this RDS because we're going to write a lot. So a rate determining step is basically the one that dictates how fast your reaction can go. If you take a look at this reaction here, this is a 4-step mechanism, wild, which means that each step gets its own peak in a potential energy diagram and its overall reaction coordinate. The slow step is step 1. So this would be our rate determining step. If you look at the potential energy diagram, I'll do it in blue so the color coding matches. This is the initial energy of your reactants for step 1. So where's the activation energy? Well, it starts at that potential energy of your reactants and it goes up to the peak. So this is EA for step 1. This is your rate determining step. But remember that enthalpy is what we call a state function, right? So it doesn't matter how many steps you take to get there. All that matters is your net energy for this reaction. So that means that if this is the starting energy of your reactants and this is the final energy of your products, this net change in enthalpy is still your net change in enthalpy for the overall reaction, regardless of the fact that each of these elementary steps is going to have its own value of enthalpy. Okay, so what does this question even ask us to do? It asks you to determine the overall reaction from its elementary steps. So what this means is we got to look for intermediates and we got to look for catalysts. Are there any things that we can cancel that are going to help us write the overall reaction equation? So we want to look for things that show up on both sides of the equation. So in step 1, our rate determining step, we have this molecule here that shows up as a product and then later as a reactant. So what kind of a substance must that be? It must be an intermediate. It gets produced in one step and consumed in the next step. I also see HOBr, and there's 2 moles of it that are produced in step 2. But in steps 3 and 4, boom, boom, we have 2 HOBrs. Excellent news. So we can cancel these things out. We can cancel these things out. HOBr must also be an intermediate, produced in step 2, consumed in steps 3 and 4. Okay, anything else? We got HBRs. All our HBRs seem to show up on the reactant side. We got O2s. That doesn't cancel anywhere else. We got H2Os, and we got bromines. So nothing else is going to cancel. We don't have any catalysts present here. So I can just start summing everything down. Steps 1, 2, 3, and 4 each feature HBr. So overall, I have 4 HBRs. I'm adding to it elementary oxygen from step 1, and then I'm producing 2 waters, one from step 3, one from step 4, and I'm producing 2 bromines. If you take a look at this, this is your overall reaction equation, overall balanced reaction equation. So that's all that this question wanted us to do. Good to go. Okay, so how can we use this information about the rate determining step, our slow step, to kind of help us out? Remember how I told you the only way to determine the rate law for an overall reaction was from experimental data? That is still true. However, the good news for us is that for an elementary step, you can infer the rate law for a reaction from its stoichiometric coefficients. So, in big bold letters, your big key idea here is the coefficients of your chemical in your rate determining step are going to equal the order of that chemical in the differential rate law equation. So if we take a look at this example here, let's first start by writing out the overall reaction, and then we're asked to suggest a rate law for each of the individual elementary steps. So our slow step is step 1. So, crazy. Okay, so our slow step is step 1, so we need to keep that in mind for when we work on rate laws, but let's just start with overall reaction. I see C get produced in step 1 and consumed in step 2. That must mean intermediate. I see D produced in step 1, consumed in step 3, intermediate. And then nothing else can actually cancel out. I've got everything else, so I just add straight down. 2 A's are present, 2 B's are present. I have an E and I have an F as my products. So suggesting a rate law for each of our little reaction mechanisms, our slow step rate would be equal to K, our rate constant. I'm going to call it K1 because this is step 1, so it's just kind of going to help with bookkeeping later. And this would be dependent upon your concentration of A and concentration of B. For the next step, the rate law for this would be equal to K2 times the concentration of C times the concentration of B. And then lastly, your step 3 rate for this one would be rate constant for step 3 times the concentration of A times the concentration of D. So there are rate laws for each of your elementary steps based on the stoichiometric coefficients. So back to that big bold term again, the coefficients of a chemical in your rate determining step will equal the order of that chemical in the differential rate law equation. So what that means is for the overall differential rate law, because the slow step is first order with respect to A, so coefficient of 1, first order with respect to A, and first order with respect to B, that means in my overall rate law, the rate orders or the reaction orders will still be first law with respect to both A and both B, because the rate law is determined upon our slow step. Okay. You guys try this one, do this. For this example, your slow step, your rate determining step is step 2, which means that if you were to write the rate law for this, you would end up saying rate is equal to K, rate constant, times the concentration of B times the concentration of C. The problem is C is an intermediate. Intermediates cannot show up in your reaction equation because they don't show up in the overall reaction. So you can still use this as a, you can still write the rate determining step for this by using substitutions, just like you would in math, right? So is there another way that we can write C? Yes, there definitely is. We know that the production of C is based off of the rate of this equation. So for this one, the rate, the rate is equal to K times A squared, right? So I can rewrite this to be in terms of A because that's how I get C. So here, this A squared, because that rate is producing C, I can actually use this and substitute it into this equation for C. So that way the rate law overall is still in terms of my reactants that appear in the overall rate equation, which means that my rate for this overall reaction would be equal to rate constant K times the concentration of B times the concentration of A squared, where I just substituted A squared for concentration of C from the step above. Okay. So for this one right here, you're given a two-step reaction mechanism. You're given the potential energy diagram for it as well. The question asks you to determine the overall reaction and also the differential rate law for the reaction. So first things first, let's identify some catalysts and some intermediates if we have any. So, ICHI produced in step 1 and consumed in step 2. That must mean that this is a intermediate. ICICL produced in this step and consumed in the next step. So I'm going to get rid of that too. And then everything else I believe is as is, so I'm just going to add straight down. So overall, I've got hydrogen, I've got 2 ICLs. I'm sorry I didn't loop-de-loop that CL, I feel like I should have. This is producing 2 HCl's and 1 I2. So there's my overall reaction here. So because this is my slow step, this is my rate determining step, which means that if I want to write the rate law for this reaction, it's based off of the rate of my rate determining, the rate law of my rate determining step. So if I write that out, the rate would be equal to rate constant K times concentration of hydrogen, times concentration of ICl, but this has a stoichiometric coefficient of 2, which means that I have to square it in my rate law there. So this is my overall rate law for this reaction, because we can write it based off of our rate determining steps rate law. Okay, so number 2, if your job were to find a catalyst for this reaction, why might it be important to know the mechanism? What's the point of a catalyst? Catalysts lower activation energy for a reaction by opening up a new reaction pathway. I guess I should have flipped that. They open up a new reaction pathway, therefore the activation energy of that pathway is lower. So why would that matter? Well, you wouldn't want to introduce a catalyst in a step that has a lower activation energy already. It would want to be introduced when you need it to speed up your slowest step, right? So you want to introduce a catalyst that would speed up your rate determining step. So need to know rate determining step to introduce a catalyst that would speed up that step. So, step 3, which elementary step would you have to catalyze to have any effect on the overall reaction? Well, it would have to be step 1. Why would it have to be step 1? Because that's our slow step. This is our slow or rate determining step. You can also see this if you take a look at this potential energy diagram. Look at the difference in activation energy. Let me highlight it here for step 1 versus step 2. Step 1 clearly does have a higher activation energy, which also helps indicate it must be the rate determining step. Higher the activation energy, the less likelihood you are going to have successful collisions. So you could also add in, like, from the potential energy diagram, the activation energy for step 1 is clearly very high. So lastly, it's telling us to draw the effect of the addition of a catalyst in another color on this potential energy diagram here. So we would be adding our catalyst in for our slow step, step 1, which means we're going to lower the activation energy barrier of step 1. So what that would mean is I would draw a little section of my potential energy diagram like this that has a lower activation energy than the one that it currently exists. Then the rest of my potential energy diagram isn't going to change at all. This is still going to be the fast step. I'm still going to end up at the exact same potential energy of my products, because it doesn't matter how you get to the end. Hess's law says the energy is going to be the same. So that's your little introduction to reaction mechanisms. Your next step is to practice. Go to the next assignment. Bye, everybody. Love you.